I'm Ryan Brown.
I'm Chad Kohler.
I'm Tim Clark.
I'm Robert Royce, and we are Team ATLiens.
ME 2110 Creative Designs and Decision Making is a course at Georgia Tech in which student teams plan and construct an autonomous machine to complete a list of point-scoring tasks. This machine must compete amongst other student teams in 2 preliminary competitions and a final competition at the end of the course. In this video, you will be walked through the creation process of our machine, the ATLien, as well as a performance review of the machine. Before we dive into our machine, let's discuss the competition rules and tasks. For the Spring 2017 competition, the set of tasks are placing a flag worth 60 points, retrieving the astronauts and rovers worth 28 points apiece, landing your spacecraft worth 15 points if landed in the safe zone, and negative 20 points if landed in the unsafe zone, and clearing your home zone of radioactive elements worth negative 6 points apiece. The machine to complete these tasks must be built for less than $100 and must fit into a 12-inch by 24-inch by 18-inch go-no-go box. It must be boxed before each round of competition. Finally, the only sources of power the machine can use are the actuators given by the course instructors and gravity. With these tasks and rules in mind, we began the planning stages of our machine. The first thing we created was a house of quality. This allowed us to prioritize the various engineering requirements and created a criteria to judge alternative designs. From our house of quality, we determined that the most important requirements were to score points, perform consistently, and generate enough force in each subsystem to not fail. After the tasks and requirements were prioritized, we created a solution matrix to drive our design process for the alternative designs. As you can see, we selected different mechanism options for the subsystems and used them to CAD the designs that you are about to see. In some situations, certain subsystem options were left out of the design entirely. Concepts for the machine's functionalities were developed using a solution matrix. 5 possible designs were explored, and each design focused on solutions for various functionalities. However, the final machine presented a simple and consistent design. This design was chosen despite its low points potential because it had a higher points minima due to its consistency. The evaluation matrix illustrates how much emphasis was placed on minimizing disqualification and amount of error per run. This selected system outscores all of the alternative designs in these categories. Design Alternative 1 has one arm with an attached gear rack and a gear with a guide rail that helps the rock collection. Weights are attached to the back of each end of the scissor arm, and they are dropped down, causing the scissor arm to extend forward to retrieve astronauts and rovers. Surface clearing arms are attached one on each side of the machine with mouse traps that swing forward to extend the drawer arms to the edge of the home zones and hit the radioactive elements out of the home zones. The prototype of this machine proved that the mechanisms were too inconsistent. Design Alternative 2 has cylindrical rolling objects that are released by the solenoid to clear radioactive elements. This machine has the advantage of being effective and easy to set up. The rock collecting and astronaut rover retrieving arm is triggered by a pneumatic actuator, then pulled back with the motor. The flag and spacecraft placing tasks were abandoned in this machine. Fitting in the go-no-go box was a concern with this machine, as well as the inconsistency of some task performances. Design Alternative 3 has solenoid-triggered extendable arms attached to a drawer slide that performs 3 tasks. The mousetrap flips the point-scoring arm to retrieve the astronauts and rovers and place the flag. The long-arm switch identifies the safe zones and triggers a solenoid to pull the launch pin out of the spacecraft storage to place the spacecraft into the safe zone. These multitask arms make the machine space efficient and easy to reset. This machine has the highest scoring potential. However, the number of components could lead to inconsistent performance and difficulties fitting in the go-no-go box. Also, it was too complex to build given the time limitations and resources. Design Alternative 4 is a horizontally oriented design with a scissor arm and surface clearing arms. A ramp is added to the top front bar of the machine to counteract the bowing of the scissor arm when it is fully extended. The scissor arm is extended when a weight is dropped down from the supporting block. This places the flag in the designated zone. The rock collecting arms drop down behind the rock sample and is retracted by a string attached to a motor. Furthermore, the surface clearing arms are folding arms held in by a pin attached to a solenoid on each side. The design was not chosen because the scissor arms were hard to work with and the solenoids were too inconsistent. The testing of the preliminary machines made before the final selected system did not go very well. The scissor arm design to reach the center mountain ridge proved to be way too inconsistent due to the bow in the arm. The rock collecting arm on the gear rack and rock collecting arm connected to a string were both too inconsistent in pulling the rock samples back into the starting zones, and both designs had issues reaching past the rock samples. Furthermore, the prototype machine used in the qualifying round used drawer sliders for the point scoring arm, but the machine had trouble fitting in the go-no-go box, and it was hard to reassemble after each round. The prototype machine scored negative 311 points total in qualifying, which resulted in seeding 60 of 61 teams. The results led to the simplifying and shrinking of the final selected system to ensure they would run correctly each time and fit in the go-no-go box at final competition. The preliminary results of the final selected system with just the point scoring arm went well. The point scoring arm consistently extended to the correct length in order to place the team flag, retrieve the astronauts and rovers, and land the spacecrafts in the safe zone. A slight inconsistency in the astronaut and rover retrieval was that when they hit the ground in the home zone, they occasionally will bounce out of the home zone and into a different home zone. Also, the solenoid did not always retract and land the spacecrafts in the safe zone, even though the solenoid fired every time. The selected system easily fit in the go-no-go box and was easily reassembled, so disqualification was never an issue.
I will now walk you through our final competition machine. The point scoring arm is fired by 2 pneumatic actuators using 2.5 psi. The point scoring arm extends to the edge of the center mountain ridge. It is held at the correct length by this string. The flag placing and astronaut rover retrieving arm is held in the machine by pressure. When the flag placing and astronaut rover retrieving arm clears the front of the machine, it is flipped forward by 2 mousetraps. It is stopped at the correct angle by this triangular wooden piece. The mousetrap is deployed, which places the team flag over the designated area. The astronaut rover retrieving part flips down onto the surface of the center mountain ridge in order to knock the astronauts and rovers into the home zone as the center mountain ridge rotates. The long arm switch detects the safe and unsafe zones. When a safe zone is detected, the solenoid pin retracts and the squash balls are released from the safe zone. The roller on the solenoid pin decreases the amount of friction between the squash balls and the solenoid pin so that the solenoid pin does not prematurely retract. The wires are placed in a tube in order to prevent tangling. Once the machine is completely set up, you simply place the protective side panel in the brackets and Velcro it to the side of the machine, and the machine is ready for competition.
For the final competition, we placed in the top third by making it to round 4, which is a huge improvement compared to the qualifying competition. The pneumatic actuators and flag arm worked consistently throughout the whole competition, as you can see in the chart. The biggest problem we had was the mechanism related to the spacecraft. The power exerted from the solenoid was not strong enough to act against the weight and friction made by the 4 spacecraft. And while we did account for this in testing, the margin of error for placing the solenoid pin was very small and therefore inconsistent. Another problem that we faced was the astronaut liked to hang onto our machine. The astronaut's arm would get caught on the collecting plate and would not drop into our home zone. While this did not score points for our team, it also prevented other teams from benefiting from the points. Throughout this project, we learned a lot of things. First of all, the key to team success is good communication and planning. In the initial stages of this project, our team was not on the same page and many all-nighters were pulled to meet deadlines. Eventually, we began utilizing the planning tools and making sure to communicate better, and this made a world of difference. We have since been able to complete tasks early and thoroughly, which is a big reason why our machine performed so much better in the final competition than in the preliminary rounds. Planning ahead was also crucial because as the competition got closer and closer, the studio became busier and busier, and it was important to utilize the time we had on the track wisely. Another lesson learned was the value of testing a lot. In the preliminary competitions, we did very little testing, and it showed. However, in the final competition, we tested our machine countless times and made sure that it worked consistently and did not surprise us. Finally, we learned the value of simplicity. In our early design subsystems, we had some very complicated mechanisms. Needless to say, these did not work consistently, and the simpler designs won in the end. Thank you for watching.
Now throw your hands in the air and wave them like you just don't care. And if you like fish and grits and all that pimp shit, everybody let me hear you say, oh yeah, yeah. Now throw your hands